this would be the third part of friction clutch on disc clutch. So uniform wear theory. As we have said earlier, when a clutch has been used for a period of time, the surface material, the frictional lining material surface, will be subjected to wear. So what happens is the pressure distribution on the surface here will no longer be uniform. Therefore, we need to consider another theory which is called the uniform wear theory. So considering uniform wear theory, now since the intensity of pressure for uniform wear theory varies inversely with the distance, that is the radius r, therefore P times R would be equals to a constant. P would be the pressure and R would be the radius of the frictional lining material. So if pressure here is maximum, then the radius that we refer would be minimum and is equals to a constant. Or if the intensity of pressure is minimum, then the radius that we consider should be maximum, then equals to the constant C. Or it can be written as P equals to C over R, where C is the constant and R is the radius of the frictional lining material. It depends on whether we are looking at the inner radius or the outer radius. Inner radius, then this pressure here should be maximum. If it is outer radius, then the pressure here should be minimum. Okay, so this is the spring force transmitted or taken up by the elementary ring. So pressure times 2 pi r, which is the length, and dr, which is the thickness of the ring. So this pressure no longer is uniform anymore. So therefore, we replace this P with C over R. I repeat once more, C is the proportionality constant and R is the radius, either is inner or is outer. So the radius times with 2 pi r dr. So the radius will cancel out. So you have the spring force or the axial force or the normal force now be equals to the constant C times 2 pi dr. So to find the spring force, to find the total spring force of the entire surface, we can integrate both sides with respect to R. Okay, so torque transmitted based on uniform wear. Okay, so as you can see from this diagram, I have put it at this radius, that is the minimum radius, the inner radius, the pressure here, the intensity of pressure is being considered as maximum, or at this point here, the radius. So at any point on the inner radius. So and at any point on the outer radius, that is R max, the pressure distribution here would be minimum. Okay, so that for you have this equation showing you that P, that is the intensity of pressure, and the radius, they are inversely proportional. So total force that is acting on the friction surface based on this equation here, we have to integrate both sides. This with respect to W and the other side with respect to R. C is a constant and 2 pi are constants too. Okay, so integrate with respect to R. So 2 pi and C are constants. So when you integrate one with respect to R, you have R. Then by inserting R1 and R2, you got the spring force is equal to 2 pi C R1 minus R2. Then taking the C as the subject now, so you will have W divided by 2 pi over R1 minus R2. Now, frictional torque acting on the ring. Now again, we know that frictional torque is equal to tangential force multiplied by the mean radius in this case. So, and also we know that the torque transmitted by the elementary ring earlier is equal to 2 pi mu PR squared dr. But remember, now the pressure is no longer uniform. So what you have to do is substitute your C over R for this part here. That is the intensity of the pressure, which is no longer uniform in this case. So you have C over R, the R deleting with this, so you have R squared becomes R to the power of 1. So you have the torque transmitted by the elementary ring now. And then if you want to find the total torque transmitted by the entire surface under uniform wear, total frictional torque acting on the friction surface, so you integrate both sides, this side with respect to R, the other side with respect to the T. So integrating this, you have R squared over 2, and then insert your R1 and R2 into the R square. Okay, so you have R1 square minus R2 square over 2. Then the 2 and the 2 here cancel out. Okay, or you substitute the C, which is equal to this, substitute C, which is equal to W over 2 pi times R1 minus R2 here. And this part here remain as R1 square minus R2 square. And we know that, okay, based on this R1 square minus R2 square, it can be written as R1 minus R2 multiplied by R1 plus R2. Okay, so if R1 minus R2 times R1 plus R2, it will cancel out with this R1 minus R2 here, remaining of R1 plus R2 times, okay, W, 2 pi cancel out. Okay, so this has been cancelled out. So you have the half, the mu, and the W, R1 plus R2 times the number of pairs of contact surface. In the case of a single disc clutch, N is always equals to 2. So this is the total torque transmitted by the pressure plate, by the clutch plate under uniform wear theory. Okay, this is all based on uniform wear theory, and we have done the uniform pressure theory earlier. Now, they are based on a single disc clutch. Now, if let's say, for example, you are referring to a multi-disc clutch, it's not much difference. It's only the number of pairs of contact surface. You have to do some modification, where N1 stands for the number of discs on the driving shaft, and N2 to be the number of discs on the driven shaft. So actually you want to find, if let's say for example you want to find the total number of pairs of contact surface, then you should take N1 plus N2 minus 1. So this will give you the number of pairs of contact surfaces for a multi-disc clutch. So the torque transmitted formula under uniform pressure and under uniform wear theory, with the N, it should be replaced by N1 plus N2 minus 1. And usually we work it out separately, and then the N represents the number of pairs of contact surface. Okay, so that is the torque. So this is the diagram of a multi-disc clutch assembly. Okay, that's all for the section today, and thank you very much for watching my podcast. And if you have any comments or questions, please put it on my comment section in my PowerPoint podcast under friction clutch. Thank you very much, and see you again. Bye bye. Thank you.